So whenever you guys are ready, can you just explain what is going on?
It's glitchy right now because we're trying as fast as we can.
Okay.
Once we have like a few particles, we'll slow down to the correct speed.
So basically this is a Lennard-Jones force/molecular simulator. We are simulating a couple of forces between inert atoms. So we place atoms in the rectangle right there, and they start interacting with each other. We can control gravity, we can add energy to the system, we can pull energy from the system.
You can decrease the bounds of the box, make it smaller.
Decrease the bounds of the box.
Get more
Cool.
energetic.
Yeah. So let's just add a couple particles to the system. So the gravity's on right now.
Yes.
So we add particles, they start interacting. I'll add like 70 for now. Do you want to resize the box right now?
So gravity makes them fall to the bottom,
Yeah.
Just resizing the box.
and then
And we can compress them. Go one out, I think. Is
Yeah,
best for
that's the next.
just if we let them equilibrate.
And then-
go one more. I think it can handle it.
Smaller?
Yeah, one more.
Okay.
Just let it
so the color of the
equilibrate for a
particles is related to
Speed.
the speed.
Cyan
Slash
is the
energy.
slowest.
Okay.
second.
So is this kind of an illustration of like an ideal gas law thing, like decreasing
Sort of.
volume and increasing?
I would even say that it's more akin to, like, based on what I've been observing, what we'll show you in a sec, it seems like it models liquid and gas more so than it would a solid. Especially when we turn off gravity, the way like water and space would kind of interact, it
Cool.
kind of floats and bunches up like that, and then you can turn on gravity and more so fills the box than retains its shape.
We have also noticed something similar to like vapor on the surface.
Yeah.
Add
Yes, make the box a little bit bigger. Yeah, and just add a bunch to get spin a little bit. So there is one glitch with the adding energy, which is sometimes when you add too much, the particles sort of hang around the top and the bottom. Not sure
Okay.
why that is, but if you add it,
gravity.
keep adding a bunch, and actually turn it back off for a second.
Gravity.
Add energy. Just add enough energy so that they're like kind of all over the place here. All right, just let them equilibrate.
They cool down. Phase change.
So they're cooling.
Yes.
And there's something implicit about the physics that we're using that cools it. We don't have to cool it ourselves. It will just cool down.
Just loses energy.
Because
we
we're not
can
like
cool it.
we're not like maintaining a constant velocity in the system or anything. So something about the particle interaction just the velocity decreases.
Yeah.
How interesting.
So if I turn on gravity, everything falls now.
So with the present amount of energy, these are forming something like a crystalline
Yeah.
structure, like
Yes.
they're in sort of.
So if you look at we'll do it one more time and then just let it settle to the ground.
No gravity. Yeah.
I don't think we need make it like add particles. They sort of clump up. You can add energy again if you want.
Oh yeah.
We can also manually remove energy if you want to show that.
That's slowing it down fast.
Turn on gravity maybe.
Turn on gravity.
And we'll just show you how it kind of settles. And it is sort of crystalline, but it is like form-fitting to the container. So
Yeah. Okay.
Until
it is.
Yeah, it is on.
It's kind of
Just slow.
Wow, that's interesting.
Yeah.
And then the particles will find, these are like, if you were to visualize the potentials, they're like kind of, they're circular. So particles will kind of ride on the top of the surface and find something like that. And sometimes they'll like, you'll see like this particle hop in there, even though we're not directly modeling that.
Oh, see, that's about to.
Yeah. So they organize themselves in a really
Lowest
even
potential.
structure.
Yeah.
Okay.
And the way we're simulating bonding is we're just checking distances, and we add an additional elastic force if a particle is within a certain distance.
Okay.
So
Oh, that's cool.
as they like pass through it, they eventually.
Is it always just the first direction minus one?
Speeds up the smaller we get. The walls basically act like a spring, so if it goes out, it just pushes out.
Okay.
It's not like a hard wall.
Yeah.
And I always think it's interesting when you watch a particle like fly off and then come in because they kind of like follow a zigzag pattern
Yeah.
to blast through the.
That's interesting.
Make it smaller.
Yeah, and try and get them vibrating really fast. Like make it pretty small.
We can add energy now.
Yeah, but even just resizing, you'll get them to, and now let it like.
Settle down.
Yeah. This might be a little bit too small.
Yeah, it's too small.
Dude, do you want to restart it quickly? I'm gonna add 60. I found it 60 was like a good amount for that box.
Okay.
Alright, go back to whatever side it was.
So every time you click, it adds
10.
10?
Okay.
Okay.
One for each iterator.
Okay.
One more out, like one bigger.
Bigger?
Yeah. Yeah, this is like, and they kind of organize really nicely. And
Yeah.
you can kind of get that, like some of them are based on the frequency of the color change, you can tell they're vibrating.
Yes.
That's sort of capturing the
I think for drawing, we
It
can,
may actually be too small for stuff.
we can define an X.
that's pretty good.
You can make it larger.
Yeah.
See that
Because
thing.
it's super
They relax
this
a bit.
way. Next one should be other function in the way.
Could turn off gravity.
So, you mentioned that you have how many iterators doing this?
10.
So basically, we're doing the first, like, I don't know. I would say the most challenging in the first like 2 weeks of this project, we spent trying to figure out what approximations could be made.
God, it looks like a liquid drop.
Yes, I was saying it looks like it reminds me of like a liquid in space.
Yeah.
Yeah. And then when we turn on gravity, it fills the
Yeah.
container, sort of. So the first portion of this project, we spent trying to figure out where we could sacrifice precision and where we really needed it.
Uh-huh.
And it turned out we could not sacrifice any precision on the position update. So when we do the position update, we take the acceleration, we have to multiply by a factor of t squared, t being the time step. Since our time steps are very small, we end up multiplying by like 10 to the negative fifth every time. And we need the precision and we need like 5.
Because each time step is like a really tiny amount, and if we cast it to anything integer, we'll lose it.
Yeah, we lose it entirely.
And
So
it doesn't update anything.
So that is done in, so that's done in C. We calculate the acceleration in Verilog and we pass it to C.
Okay.
So the split here is that the force calculations are done on the FPGA, and the numerical integration is done on the ARM, which is the classic way of breaking it up.
Yes.
Yeah, and then to calculate, so we do it's mostly just multipliers. I think each solver uses 8 multipliers.
Yes, 8 multipliers, 10 solvers.
10 solvers.
6 for the overhead update.
And then each iterator has an associated lookup table. So we're not using like dual port lookup tables or anything like that.
Yeah.
We just
Okay.
have-
We have 10 for it. It's not.
well, there's 10 different ones. 'Cause
Yeah,
we're-
we can't make one with 10
Yeah.
ports.
In the lookup table, the way we did that originally, it was just huge, and we were doing like a very high precision lookup. We realized we didn't need as much precision on the like when particles were far away from each other. So we just generated some Verilog in MATLAB, just with like text, printed it out.
Okay.
And we did like if the distance is, I think the only distance we ever care about, or the only time we would be using the lookup table is if the distance is like 16 pixels. So for like 0 to 5, we have lookups every like point corresponding to every 0.2. Every 0.2 pixels, so to speak, because we don't treat pixels as we don't treat positions as integers for the whole calculation. We really cast
Right.
at the very end, and then we do a lookup of like is it like
Two
a lookup of 2 after that, because it ends up not really affecting the physics at all.
Okay.
Kind of not noticeable.
Yeah.
It's impressive.
It really is.
It's really impressive.
But yeah, it ended up
keyboard.
Yeah, ended up looking really cool. And then, so if you can you resize the box to the biggest size?
Biggest?
Yeah. So we're doing 10.17 fixed point format, like 1 sign bit 9 for the. We only ever use the most significant 10 bits for like position essentially.
Okay.
Because those are the largest numbers. But because we only have 9 bits, we could only utilize that size of the VGA. I mean, we could have translated it before we drew to the VGA.
Okay.
But that's what's limiting the box.
Sure.
But
Okay.
using the mouse would be like difficult because math would be complicated.
One option we consider is like manually scaling it as well, just like multiplying everything by 2. But then you lose a little bit of precision on the movement, or it like looks a little bit
Okay.
more clunky.
The code itself can like handle different steps and everything.
That's very.
And then I'll show you what the time lapse looks like. We
Yeah,
didn't record it for
it's
too
like,
long, so it's
500 particles.
it slows down quite a bit once you get up to like the
Oh, more than 100. 120 is like.
200 works pretty well.
So the frame rate's dropping
Yes.
considerably here.
So
Okay.
we did a little time lapse of what 500 particles would look like. This is just placing them. We didn't record it for very long, but
I'll have you send me that and I can add it to the end of the video. but-
okay. Yeah, then it stops there.
Then it stops.
Really cool.
So it's stable for very many particles.
Yes.
Very nice.
Yeah.
Awesome. Thank you guys.
Like now
Yeah, this is just
Box
regular.
is too small.
Cool.